So we're on lesson 205. This video is actually going to serve for lesson 206 as well, because 205 has you read the first part of chapter 6, and then 206 has you complete chapter 6. So there won't be a video for 206. However, this video kind of covers both chapters. So you're going to see we're going to start talking about grounding here, and we're actually going to spend a lot of time in year 3 covering this in great detail. In fact, you spend about a whole semester on just grounding. So this is, very much an overview because it is a tremendous topic for sure. And you guys can see all the different objectives they have. And we're just going to kind of graze into the surface of it here to begin with. So it tells here increasing the impedance of the ground fault path reduces the amount of current that flows in the circuit. So what we need to consider here is we want a low impedance ground fault return path. If we do have a ground fault, we want effectively as much current to flow as possible, because as we said with an inverse time breaker, which is probably most common, the higher the overload, the quicker the breaker is going to trip or open up. We want a low impedance ground fault path. It's going to allow a lot of current to flow in a short amount of time. The more current, the faster that overcurrent device actually trips. So they go in here to talk about a grounded conductor. Typically, we're used to the grounded conductor. When we say that, we think right away neutral, and probably 99% of the time that is fine. That's correct. However, there are some sort of unusual voltage systems, and we did mention this once before. This what they call a corner grounded delta system. They actually ground the B phase here. It's also called a dead man's leg, as I said before, because listen, if you take a voltmeter, measure from B phase to ground, you're going to read 0 volts because this is intentionally connected to ground. Obviously, that can be a big deal. That's why they're very, very uncommon. But again, more on that specifically later on in the year. But grounded conductor does not always mean neutral conductor. Keep that in mind. So the next term they want to hit here is what they call the EGC, the equipment grounding conductor. So that conductor provides a low impedance ground fault current path between electrical equipment and enclosures and the system grounded conductor and grounding electrode conductor. So basically that's the wire that when you pull a green wire to your circuits, that's a equipment grounding conductor. The ground that goes from your panel to your receptacle to your light to your motor, those are all examples of equipment grounding conductors. The equipment grounding conductor is connected to the system grounding conductor to facilitate the operation of the overcurrent protection device by providing that low impedance path for fault current that we talked about in the previous slide, right? We want that low impedance ground fault return path that's accomplished via the equipment grounding conductor, right? We have a short anywhere here. We'll send that ground fault return path. In this case, the short occurs here. It goes through the metal housing, through the equipment grounding conductor, back to the, in this case, the neutral bar, through the main bonding jumper, which we'll talk about. So essentially a lot of current flows through that breaker, which causes it to trip. So not to be confused with the equipment grounding conductor, the EGC, we now need to talk about the GEC, the grounding electrode conductor. So that's the conductor that essentially connects our equipment to the grounding electrode, right? The grounding electrode conductor. So what's a grounding electrode? They're kind of giving us these examples sort of in reverse here, but your grounding electrode are the things that actually connect to the physical ground. So your ground rod, in this case, we have rebar. You can think of underground metal water piping. Those things are all grounding electrodes. Well, the conductor that connects to those is your grounding electrode conductor. Again, not to be confused with your equipment grounding conductor. They're going to come in here and mention to us that separately derived systems do not have any direct electrical connection between the supply system and the separately derived system. Basically, what are we talking about? If I have a transformer, very common, we have a 480 transformer that steps down to 120 to 208. There's no physical connection between the primary and secondary side, as we'll learn later on in the year. Because of that, we have a separately derived system. We actually have to basically apply our grounding electrode rolls and conductors, again, we need to have a separate grounding electrode conductor in this case. Right? So the GEC and grounded conductor can be connected at the source of the separately derived system or at the first disconnecting means. What are we talking about? That's your main bonding jumper, right? So your grounding electrode conductor, again, think of your ground rod, your water pipe, can be connected, and yeah, sorry, the grounded conductor. So again, that's now essentially, again, in most cases, you're neutral. We have a GEC, we have a grounded conductor. What do we put between those two at our main panel? Most of us hopefully know at this point is a main bonding jumper, right? We can bond at our first means of disconnect. You guys are used to hearing that terminology. So they're going to tell us here specifically that can actually be done at the first disconnecting means or at the source of the separately derived system. So in this particular case with the separately derived system, 480 panel goes to a transformer, steps down to a 208 volt panel. I could bond here or I could bond here. I'm going to tell you guys, for me, if this is just a simple, panel board, a lot of times they have just a simple bonding screw. Why not do that for your main bonding jumper? I should say for your bonding jumper for your separately derived system. You can do it here or you can do it here. Either is actually acceptable. Grounding electrode system shall be created for each separately derived system. That's what I mentioned on the first slide talking about separately derived system. The requirements for grounding portable generators are included in 25034. I'm not going to go into depth on that other than to say there are actually requirements for grounding portable generators, believe it or not. Metal elbows installed in non-metallic raceways are not required to be connected to the grounded system or electrode where they are at least 18 inches below grade. This is a big one here, guys. Easy point to mess up. A lot of times we'll put in a rigid elbow to help with our pull so we don't burn through a PVC 90. If this is PVC here and PVC here, this pipe is now technically isolated from our electrical ground. If this were any less than 18 inches below grade, we would have to basically drop out of this cabinet with the ground, and they have certain connectors that we could use to actually bond this metal pipe that's isolated by this non-metallic pipe in order to actually connect it to our grounding system. But if we're 18 inches or lower, we don't have to worry about it. Short sections of raceway could pose a threat to personnel. That's what he's talking about. Again, we have NM cable, short section of raceway. They are permitted to be installed without being grounded. However, that doesn't mean they're free from danger by any means. So it should be something that you definitely take in mind if that's somewhere that's actually possible for somebody to be in contact with it. We may need to take some extra grounding provisions, right? Short sections of metal enclosures or raceways are permitted to be installed without being connected to the equipment grounding conductor. They're going to tell us here. This gives relief from the grounding to those installations in which the enclosure or raceway is merely used to provide a support or mechanical protection. However, the term short section is not defined. So this could lead to some confusion in the field, and more importantly, some installations that pose a threat to life safety. So this one's going to come down to the AHJ, the authority having jurisdiction there. But by code, we don't technically have to ground sort of this guy in this case, right? It's just kind of a sleeve. So I'm not going to read all these, but they actually give 14 different types of equipment grounding conductors. So believe it or not, we don't need it to actually be a wire. I mean, in today's day and age, it almost always is a wire. But especially years ago, they used the actual raceways of varying types as equipment grounding conductors. And that's still allowed. I think you're going to have a lot of explaining to do, but and by most specs, you're not allowed. But by the code, you are still allowed. You have 14 different methods all listed out here that could be used as equipment grounding conductors. 4 methods may be used to bond service equipment. Really what it comes down to here with these various different bonding bushings and lock nuts, as a quick sort of rule of thumb, if you have concentric or eccentric knockout, so in other words, you haven't knocked it out all the way, your pipe is not considered a good electrical connection. You will need to get into some kind of supplemental bushing or lock nut in order to actually ground that pipe if you have a concentric knockout that's not knocked out all the way. Sorry, I skipped ahead there. So uh, they're going to talk about a inter-system bonding termination. That's this little guy. This is kind of a residential thing mostly, but you're going to see this little ground bar put out by the service. It's really meant for the cable and phone companies to bond to. I'm not going to spend a lot of time on that, but it is actually required to be there. The main bonding jumper is the connection at the service equipment that ties together the EGC and the grounded conductor and the grounding electric conductor. So that's, again, if you have just a panel, that's that bonding screw or kind of that strap that goes to the can and to the neutral bar. But it's basically the point where the neutral bar or the grounded conductor, again, in most cases it's a neutral, can be connected to the ground and the casing and the housing. You're really only allowed to do that at your main service disconnect, and if you have separately derived systems at that first disconnect as well, right? The equipment bonding jumper is a conductor that connects two or more parts of the equipment grounding conductor. So that's really just a bonding jumper to go from one metal piece to another. That's kind of a general term. All grounding electrodes must be bonded together to form a grounding electrode system. So we can't have like isolated parts of our grounding system. Everything must be connected throughout the entire building with very, very, very few exceptions. Per 250-64, the bonding jumper for a grounding electrode conductor raceway shall be the same size or larger than the required grounding electrode conductor. Grounding electric conductors are never required to be larger than 3/0 or 3/0 copper or 250 aluminum. That's a nice one to maybe keep up your sleeve. Again, the specs may say differently, but by code, that's what we have. The grounding electrode to a ground rod or other electrode need not be larger than a 6 gauge. So to a ground rod, you don't have to run larger than a 6 gauge copper. That's a big one too. You don't know how many times somebody tried to insist on larger. The code says 6 is all you got to do. 6 is all that ground rod could handle. It could handle the same as a number 6. So keep that one up your sleeve too. Several EGC shall be provided when flexible metal conduit is used to connect equipment. Essentially, if you're using your conduit as your ground, which hardly anybody does, if your flex is longer than 6 feet, you need a supplemental ground basically to jump out around this. They don't consider that flex to be suitable as a grounding conductor. If multiple circuits are run in a common raceway, only one EGC based on the largest size must be run. So what's the biggest circuit in that pipe? That's how you need to size your ground, and you only need one ground. We don't need to run a separate ground for all these circuits. In this case, looks like a 60 amp is the largest, so I need a ground according to a 60 amp circuit. All right, so again, that was a very quick overview. There's a lot to talk about in grounding. This actually occurs over 2 lessons for you guys, and you're going to hit it way deeper in year 3. But again, that's kind of the crash course of it all. Take your time, read through it. Obviously, it's very important stuff. Article 250 is one of the longest in the code, so there's a lot to digest.